and welcome to the Mathematician's podcast, the podcast where we follow the fascinating stories behind the people that count in the history of mathematics. I'm your host, Benjamin Cornish, and today we're diving into one of the oldest mathematical texts in human history, the Rhind Mathematical Papyrus, and the remarkable scribe Ahmes, who preserved its wisdom for posterity. For the next 20 minutes, we'll explore what this ancient Egyptian document can teach us about how mathematics was practiced nearly 4,000 years ago, and why Ahmes deserves the first spot among the greatest names in mathematical history. But before we begin, let me preface this podcast project with a set of intentions, scope, and limitation. Who am I? Well, for starters, significantly underqualified to present a history podcast. I've had to research all of the historical content as I go. Instead, I am myself a mathematician, albeit not one worthy enough to deserve my own episode. Instead, I'm a mathematician in that I love mathematics. I happen to have a master's degree in maths from the most prestigious university in Wales, Aberystwyth, but this is not where I did the majority of my learning. You may assume I am a glitzy celebrity, given that I have a podcast with at least one listener. But my day job is as a maths teacher, where I have the delight of talking about maths for over 5 hours a day. Sadly for me, this is about 60% talking about trigonometry and the other third fractions. Initially, I was hoping to write a podcast script for every significant mathematician in history. A quick look over at mathgenealogy.org will tell you that there are in excess of 300,000. Curiously enough, this source logs every mathematician's name, along with their teacher, students, and key documents they have authored. A humbling look at the history of mathematics. Clearly, this would be untenable, so instead, I have devised some criteria to help me choose who to include. Given that I am a maths teacher, I'm going to make myself the target audience. To that end, I will only intend to talk about mathematicians whose work is reasonably understandable. On a similar vein, I will restrict myself to work that is readily available in English. I appreciate that this will ignore the weighty contributions made by different cultural spheres in parallel to those of Europe. However, I feel that the history of mathematics in China, India, and other cultures with a written tradition deserve their own examination by someone better qualified than me. I would like to reserve the right, however, to dip into these traditions where I find a character who I would like to share. My second criterion is that a body of work needs to be rich enough for me to present a full podcast. For instance, Leucippus, what a very interesting mathematician, physicist, and philosopher. However, the majority of his life's work was given to the latter two. He is considered the father of atomic theory. Alas, he didn't provide the mathematical calculations to support his theory, so he will be written out of my history. Whilst many mathematicians have another day job, which are often very interesting, they need to have pushed the world forwards in order to be on the list. Beyond this loose set of rules, I will be trying to highlight every character I can, in chronological order. So let's start somewhere in the middle, at the beginning of recorded mathematical history. Naturally, a better place to start history is in the present and work backwards. In this way, we know exactly what happens, and then move towards the less clear. In fact, I can do one better and discuss the future. In my time as a maths teacher, I have brought delight and fear to around 500 pupils. Let's do a quick Fermi approximation. The population of the UK is around 80 million, so about 1 million per age. That means for students aged 4 to 16, there are 12 million kids. Each 30 children has one teacher, although with the current economic climate, it's closer to 35. So that means there should be about 400,000 teachers. Now, half of those are primary, and only about 10% of the remainder are maths teachers. So that leaves 20,000 maths teachers in the UK, and that is 0.025% of the total population. Applying a quick binomial distribution over the 500 pupils that I have taught so far, that gives a 12% chance that at least one of my students will go on to be a maths teacher. Perhaps closer to 50% by the time I retire. Or in the more recent past, I've had around 10 people teach me maths, Shout out to Dr. Noble, who showed me what mathematics really is. Following Dr. Noble, who, despite making significant contributions to inequalities or some form or other, I never really understood at the time, he probably won't get his own episode. But Dr. Noble would have been one of a few thousand that his teacher taught. And that teacher would have been taught by someone else, and they must have been taught by someone. In fact, I would go so far as to say that there are very few people who were not taught maths. Ramanujan might be a quirky exception. And those who are not taught are the people who made the great discoveries for themselves, creating new branches of mathematics. I can tell you, the differential equations I teach now are significantly more involved than those Newton studied as a child. But look, we've just crafted a proof by induction. I was taught maths. Every person who teaches must have been taught by someone first. Therefore, there is a direct pathway between me and Ahmes, the first recorded teacher of the ancient Egyptians. Quite possibly the first ever pyramid scheme. Well, maybe the second. The Rhind mathematical papyrus is one of the most significant mathematical artefacts from antiquity. It was named after Alexander Henry Rhind, a Scottish antiquarian who purchased it in 1858 in Luxor, Egypt. It's now housed in the British Museum. Measuring about 33 centimetres tall and over 5 metres long, this scroll is essentially a mathematical textbook. It contains a collection of problems and solutions, offering a window into the mathematics of ancient Egypt. The papyrus is divided into several sections, covering topics like fractions, arithmetic operations, geometry, algebraic equations, and even basic principles of proportions. It's fascinating to see how the ancient Egyptians approached these topics without the modern conveniences of algebraic notation or calculators. I really should give a mention to the title included in the work. After all, Ahmes didn't name it after an 18th century Scotsman. Instead, it is delightfully called Direction for Obtaining Knowledge of All Dark Things, which is what I will now on right at the top of my whiteboard in class. Now let's talk about the man behind the papyrus, Ahmes. Born around 1500 BCE, his name appears on the document, making him one of the first mathematicians in recorded history whose name we know. Ahmes wasn't the original author of all the mathematics in the papyrus. He was more like a curator, copying and compiling mathematical knowledge from earlier sources. He claimed himself his source material dated to around 2000 BCE, although it is likely older still. But Ahmes wasn't just a scribe. He was a teacher, or as we prefer to refer to them, an absolute legend. He described the papyrus as being written in correct form, indicating his dedication to accuracy and clarity. He wanted to preserve this knowledge for future generations, and perhaps elevate his own status as an expert mathematician. Not that I would ever be guilty of such an indulgence. So what kind of problems do the Rhind papyrus solve? Let's dive into a few examples to understand how the Egyptians thought about maths. Unit fractions. Ancient Egyptians didn't use fractions like we do today. Instead, they used unit fractions, where the numerator is always 1. For example, instead of writing 2/3, they would write 1/2 plus 1/6. The Rhind papyrus includes tables to help convert fractions into unit fractions. These tables were essential for everyday tasks like dividing food, land, and labour. Curiously enough, we now know that all proper fractions can be written as the sum of unit fractions. Let's do a quick proof. Let a over b be a proper fraction with a less than b. Find the largest fraction, smaller than a over b. The largest unit fraction, less than or equal to a over b, is 1 over the rounded value of b over a, where b over a is rounded up. We shall call this 1 over n. Noticing that 1 over n is less than or equal to a over b. Therefore, we can subtract 1 over n from a over b, and let's say that a dash b over b dash is the remaining fraction. So a dash over b dash is equal to a over b, subtract 1 over n. Well, we can simplify this definition of a dash over b dash as an subtract b over bn. But since a is less than b, it follows that a multiplied by n subtract b is less than b multiplied by n, so a dash over b dash is still a proper fraction. Repeat this process. The process will eventually terminate because the numerator of the remaining fraction strictly decreases at each step and the fractions are positive. The algorithm generates a finite sequence of unit fractions whose sum equals a over b. This constructive process demonstrates that any proper fraction can indeed be written as the sum of unit fractions, completing the proof. Now, that was difficult to follow, so let's do an example. Suppose that 5/7 is the proper fraction. Well, 5/7 is equal to a half plus something. I can then write 5/7 is equal to 1/2 plus k, or k is equal to 10 over 14 subtract 7 over 14, leaving you with 3 over 14 as the value of k. So 5/7 is 1/2 plus 3/14. Now we turn to 3/14 and we notice that the largest unit fraction we can subtract is 1/5. So 3/14 is equal to a fifth plus j, and therefore we can write j as 15/70 subtract 14/70, leaving you with 1/70. Thus we have finished 5/7 is 1/2 plus 1/5 plus 1/70. On geometry, one of the most famous problems involves calculating the area of a circle. The papyrus approximates the value of pi as 3.1605, which is remarkably close to the true value of pi, with less than 1% error. Although the approximation is done in delightful language, common in the ancient style, a circle's area stands to that of its circumscribing square in the ratio 64/81. Remembering here that a circumscribing square is one drawn around the circle so that each length is a tangent to the circle. If we take a unit square, area 1, and inscribe a circle, the circle's radius will be 0.5. The area we know will be pi r squared, or pi over 4, which we could set equal to 64/81, multiply by the 4, and this would yield pi is equal to 256/81, which is our 3.1605. Another example is determining the volume of cylindrical granaries, a vital calculation for managing food supplies, which it gives as volume is equal to 1 subtract 1/9, there's that unit fraction, multiplied by d, the diameter, all squared multiplied by h, the height. Again, using the approximation of pi as before. You might notice, however, that this version of the formula only requires the unit fractions, and yet still, very accurately, predicts the value of pi. On practical applications, many problems on the papyrus are practical. For instance, there are problems relating to dividing loaves of bread amongst workers, calculating wages and measuring fields. One particularly intriguing problem involves finding the slope of a pyramid, what we today call the seked. This shows how geometry was used in monumental architecture, like those great pyramids. Now, you might be wondering why I have included or even begun with Ahmes and such an ancient scroll of maths problems. First, it highlights the continuity of mathematical thought. Many concepts found in the papyrus, like proportions and basic geometry, laid the groundwork for later mathematical developments in Greece, Rome, and beyond. I would like to immediately dispel the myth that we are so much smarter now than our ancestors. Yes, we have more knowledge and can store and pass on this knowledge in better and more efficient ways, through podcasting, for instance. But our ability to solve problems is no better now. Arguably, it has become worse. I have a brother who loves his conspiracy theories and is convinced that the pyramids were built by aliens. One reason people come to believe this is they doubt the ancients' ability to construct things with such accuracy and care. I wanted to start with Ahmes, as this is the first piece of recorded mathematics, and yet it is already far more technical and beautiful than many would assume was available for the time. Who can say when maths started? But we can certainly say it was in full swing by 2000 BCE. Second, the rhymed mathematical papyrus offers a glimpse into the intellectual world of ancient Egypt. It shows us that mathematics wasn't just a theoretical pursuit, but a practical tool for managing society. And finally, the papyrus reminds us of the human element in mathematics. Ahmes wasn't just solving problems, he was preserving knowledge, teaching future generations, and contributing to the story of human ingenuity. Ahmes' work endured because he took the time to record it so meticulously. His legacy reminds us of the importance of documentation in advancing knowledge, and using the right language and notation. Without him, much of what we know about ancient Egyptian mathematics would have been lost. In a way, Ahmes is a symbol of how mathematics transcends time and culture. The same problems he solved with papyrus and ink still resonate in our digital world today. And that's all for today's episode of the Mathematicians podcast. I hope you enjoyed this journey into the ancient world of numbers and learned something new about Ahmes and the rhymed mathematical papyrus. Join me next week, where we will be discussing Thales and his angles inside semicircles. You'd be right to assume it will be a good one. Until then, goodbye. The music today is Danse Macabre Finale by Kevin MacLeod. You can find more information in the show notes.